Hey everyone, welcome back to Take You Forward, where we are taking you forward. So today we will be solving DP16. So what is the pattern of problems that we are solving? DP on subsequence is what we started on DP13. I think DP14 is where we started. We did DP15, we did DP16. And if you remember, all of these things were based on a problem subsets sum, right? Where we were basically given a target and we are being asked if that target is achievable or not, and these couple of questions were follow up of the question DP of 14. So in order to understand DP of 17, I'll highly recommend please do all these three problems, then only start DP 17 because it's an entire playlist. If you skip any of the videos, you might miss out on a lot of things. So DP 17, without wasting any time, let's check out the problem. So over here, it's being given that you have to count the number of subsets. So what is the problem statement? You're given a zero based indexing array of positive integers. Again, very very important, of positive integers. Now in the previous video, a lot of people were commenting what if the elements are negative and everything. So I'll be talking about negative in the later half or the last stage of the video, where I'll be telling you if it's negative, how do you think, how do you modify DP. We'll be talking about all of that, but in the later half of the video. Okay, so you're given an array of positive integers, and you have to tell how many different ways of selecting the elements from the array are there, such that the sum of chosen elements is equal to target number tar. Okay, so basically they are saying key, let's take an example. The first example is 1 2 2 3. So this is the array given, right? And they're giving you a target over here as 3. So how many subsets? Now there the question has been changed. Now, instead of saying does there exist a subset, like in all the previous problem it was does there exist a subset which gives you this particular sum. Now instead of that, what now they are saying is count the number of subsets. Yes, they've just changed the problem and they're asking you what is the count of the number of subsets. So I can say one of the possible subsets is 1 and 2, where I pick this one and I pick this 2. And if you know, if you pick these couple of elements, you're bound to get the target 3. The another one is again 1 2. Now they might look similar, but this time it is formed by picking this one and this 2. So I picked two different elements to form this 1 2. Yeah, the subsequences might be same 1 2, but doesn't matter. I want the unique elements to be picked, like this is 1, this is 2, so it's a different subsequence. If this one and this 2, it's a different subsequence. Make sense? And the other one can be 3. So if you see, there are in total of 3 subsets. Yes, in total of 3 subsets that give you the total sum as 3. So the question is you have to count the number of subsets. Now what is the prerequisite to solve this problem? Definite prerequisite is DP14, where I have taught you about how do you approach subsequence problems, about the pick and the not pick, or take or the not pick technique. That's the first prerequisite. And lecture 7 of the recursion playlist. The recursion playlist link is in the description. Lecture 7 of the recursion playlist. Now, in the lecture 7, I told you whenever there is a problem related to count, yes, whenever there is a problem related to count, you write the function, and in the base case, whatever is the condition, if the condition is satisfying, you return 1, and if the condition is not satisfying, you return 0. This will always be done in all the count problems I've told you in the lecture 7, right? And what did I tell you? If there are multiple function calls, then all the function calls addition will be the number of ways that will be returned. So these couple of things I've told you. If there is any question that tells you to count the number of ways, always in the base case there will be return 1 or return 0, because you're basically trying out every possible choices, and at the end of the day they will tell you if it's possible or if it's not possible. And these are the ways. You basically add up all the ways and you return that, right? So what I can say is, okay, the problem is count. So we know this is the pattern of count, but you have to write the recurrence. And what are the rules that I've taught you to write the recurrence? Can you tell me? The first rule is if it's an array, then, and if you're dealing with subsequence, you know, you have to express the recurrence in terms of indexes, because it's an array. This time it will be array index. And what are we looking for? We are looking for a specific target. So we are looking for something, right? So that something will also be part. So that's a thumb rule, like always express everything in terms of indexes. It can be grids, it can be 1D array, it can be 2D, it can be 3D. The thumb rule is the first parameter will always, like you'll see in almost all the cases, it will be indexes. And the other one over here, since the question is revolving around target, it will be target. So your recurrence will be expressed in terms of index and target. What is the third rule? Explore all possibilities. We can be talking about this afterwards, but that is the third rule. Explore all the possibilities. What is the third rule? Sum up, sum all of them up, sum all of the possibilities up and return. Why is this the third rule? Because the question stated count the total number of ways, correct? So can I say this, since the array is 1 2 2 3, and if I just write the array and the sum that I'm looking for is 3, can I say this if I'm writing, remember this, f of n minus 1 and 3, if I write this, or f of n minus 1 or sum, if I write this, what does this signify? This signifies till here, like in this entire array, can you get a subsequence, like how many subsequences are there which will give you a sum s? I repeat, if I write 0 1 2 3 till the third index, till third index, how many subsets will give you the sum equal to 3? That is the meaning of f of n minus 1 3. So if someone is calling f of 3 comma 3, that means till the third index, how many subsequents are there that gives you sum equal to 3? That is the meaning of the recurrence, right? So if I write this f of index comma sum, there will be definitely a base case. Now we know if we are dealing with the indexes, something is for sure. If you're dealing with indexes, the indexes, we're starting from the backside, which is we are starting from 3. So we'll move here, then we'll move here, then we'll move here. So this is the end point where we will move, right? This is the last position that we will move. Again, a very common thing that you've seen in almost all problems, in all the index problems, either if you're starting from the back, it's going to be index equal to 0. If you're starting from the front, it's going to be the last index. That's what the base case will be. Now, what did I tell you in count pattern problems? Lecture 7, guys, lecture 7. Nahi. If you have not seen, it's your fault. Go back and watch it. Lecture 7 is the most important lecture in the entire universe. Kuch bhi bolo. Like, this is the most important lecture if you're solving any problem on recursion, DP, anything. Lecture 7, man. Lecture 7. So, return 1 if the condition is satisfied. So, we are at the base case. Now, we need to write something which returns 1 and something which returns 0. Just keep it apart from some time. Keep it apart for some time. We will think about this afterwards. Like, what are the conditions on which we will return 1 and on which we will return 0. We'll think about that after some time. First thing is done partially. Explore all possibilities. In subsequences, what are the possibilities? One is the not pick, where you say that guy will not be part of the subset. That is very obvious. The other one is the pick, where you say that this guy is going to be the part of my subsequence. We have already done in the subset problem, right? So if I say not pick, I am not picking that. So basically, if I'm at index, if this is the array, and if I'm at this index, and I'm saying on this array, can I get this sum? So I'm saying let's not pick this. I'll not pick this guy. So the remaining portion of the array is this much. This much. So I'll go one lesser, right? So I'll go one lesser with the same sum because I have not picked that into the subset. Perfect. When can you pick is my question. Assuming as of now you have not picked it, so let's keep it at 0. Why 0? Because we are adding up. We are looking for number of ways. So we'll keep it 0. So we have a 0, right? Now the question arises, okay, when can we pick up? So again, let's understand. If the summation is 3 and the element over here is 2. So I'm saying till here, on this array, can you get the summation equal to 3? So if I'm trying to pick, I can pick 2. I can. But if I make this 6, if I make this index 6, can I pick it? Because I'm looking for a sum equal to 3. Can I pick a 6 into my subset? that will be of no use. So I'll be like, if array of index is someone lesser than s, then probably I can pick it. Then probably I can pick it. And if I'm picking, let's understand what will happen. If I am picking this index, so over here I was looking for a index and sum. That means in this array I was trying to form this sum. So if I decide that I will take this guy into my subset, then the array will be reduced, which makes it f of index minus 1. But if I take this into my, won't the sum that I'm looking for will minimize? It will. So why don't you minimize? So I'll be like, okay, f of index minus 1, and let's minimize the sum by a of index. So the sum will also be minimized. So these are the two patterns. Again, we have been seeing this in all the subsets problem, not pick and tick pattern. All subsequence problems will have not pick and tick, where you say, okay, I don't pick it, so it stays still the same, and if I pick it, it is going to reduce. So what was the pattern of problem? Count. And in count, what do? We add up, because how many choices do we have? We have one choice as not pick, we have another choice as pick. So you're going to add not pick and pick. You're going to add pick, not pick and pick. So I can say, yes, I can say you're going to return pick plus not pick. So this is a choice, this is a choice. If this choice gives you some subsets, take it. This choice is going to give you some number of subsets, take it, and add them up to get the original answer. So we have almost done the last couple of steps. But still, figuring out return 1 and return 0 is left. Okay, so what does index of 0 signify? Let's understand this in deep. So if I am standing at an 0 and I come up with a sum, if I come up with a sum, when can an array having a single element? Because if I am standing at the index 0, it eventually means that it has single element. Makes sense, because if I'm standing, then the array has a single element. And if I'm having a sum, when can this guy give me this sum? I'll be like, if this sum value is 2, this also has to be 2. If this sum value is 4, this also has to be 4. If this sum value is 0, then also it's possible. Even if it's 4, and the sum value is 0, it's still possible. Why? Because I am having a 4 over here, and I'll say I'll not pick it. So probably you can write one more case of if at any moment sum becomes equal to 0, you can also return 1. So that's one more counting case that you will add if at any index sum is equal to 0. So now the base case will be slightly different. It will be, we are at index 0 and f of 0 sum. So in order for this guy to give me this sum, this has to be s. This has to be s. So I can say if, or I can say in short, return array of index is equal to s, then only this guy can give me a subset. Then only it will return a 1, otherwise it will return a 0. Make sense? I'll repeat again. I said if at any moment I get the sum, it's a subset. Or if I reach the last index and I'm still left out to form this s, this guy has to be s. This guy has to be s. There is no other option. And then only I'll count it. So I just make it equal and I count it as 1. And if they are not equal, then I'll return 0. So automatically return 1 and return 0 have been covered. So that's how you do it. You either return 0 or 1. Now this is exactly similar to DP14. If you remember, this is exactly, yes, point to point similar to DP14. The only slight change that we are doing is we are counting it instead of doing, in that DP problem, we did pick or not pick. We did this. Why did we do this? Because we were looking for if this choice gives you answer or if this choice gives you answer. Over here, we are looking to count how many choices are giving you answer. Thereby, sum it up. Makes sense, right? So what? So we have written a recursion, right? So what will be the time complexity for this? Definitely we go of 2 to the power n, because there are two choices for everyone. You say you are going to pick it, or you're saying that I'm not going to pick it, man. No matter what happens, I am not going to pick it. I'm like, that's fine, that's fine. Let's not pick it. So 2 to the power n is the number of choices that you can have. How about the space complexity? That's definitely an auxiliary stack space of O of n. Now, can we memorize this? Yes, we can, only if there are overlapping subproblems. Yes, only if there are overlapping subproblems, and we know that there will be overlapping subproblems. We have been seeing that, but still, in order to understand this algorithm of count better, because we are going to deal with a lot of problems in count, only for this problem I'll be drawing the recursion tree, so that the count recursion tree is clear to you and you get a clear visualization. How does that work? So let's take the array to be 1 3 2, and I'm looking for the sum as 3. So I've shrinked the array to this. So where do I start off with? I start off with the index 2 and 3, because this is where I start off, which is 0 1 2 index, and with the sum 3. What are the options? I say I'll not pick, or I say I'll pick, right? So if I don't pick, I'll move to the previous index with the same guy, same sum. And if I decide to pick, I'll pick this guy too, and I'll be left off with the sum 1, because if I take this 2 into account, the sum will shrink by the value 2 and it'll give me this 1. This is one way of pick. This is one way of not pick, because if I'm not picking, then I'm just moving across. Again, there'll be two ways, pick and not pick. So I am at index 1 and I'm saying I'll not pick. So I'll move to index 0 with 3, and I'll move to index 0. Over here, let's understand what happens. You are saying pick at index 1. Index 1 is having 3. So 3 was the initial guy. You took 3. So this is what happens, 3 minus 3. Thereby 0 comma 0. Okay. Now this is 0 comma 3. So you have reached the index 0. That means you have reached here, and you are still looking for 3. You're still looking for 3. Can you obtain 3 from here? No. So you say this is not a possible way. Make sense? This is definitely not a possible way. You're at f of 0 0. You have achieved your target. You have achieved your target. Let's look at over here. You have achieved your target. So you're going to return a 1. You have achieved your target. So in total, this choice, the non-pick choice gave you 0 subsets. The pick choice gave you 1 subset. So this in total gave you 1 subset. Perfect. Now you're having 1 comma 1. Again, it will have two choices of not picking up, of picking up. So if you decide to not pick up, you'll go to 0 with 1. And if you decide to pick up, can you pick up is my question. You can't pick up. You can't pick up. Why? Because at index 1, you have a 3 and you're looking for something as 1. So you can't pick up. The pickup option will not be there. The pickup option will never be there. So this guy will be 0. The pickup option will be 0. You see over here, the pickup option is 0. Just see, pickup option is 0. You can't pick up. This line will not be executed. So the pickup stays as 0. What about this? You are at index 0 and you're having a value 1. So you got that value 1. So 1 equal to 1. Thereby this returns 1. So a not pick choice gave you 1. A pick choice gave you 0. So in total, you got 1 subset. Now over here, the not pick choice give you 1. The pick choice give you 1. So you sum it up and you get in total of 2 choices. So the number of choices over here is 2, and that makes sense because one is 1 comma 2, the other is 3. So that's how the recursion works. And remember, the recursion will go like this. Remember recursion? This is how the recursion goes, man. Perfect. So we did not see any overlapping subproblems here, but if you take the array to be bigger, you can observe overlapping subproblems. So now it's time to definitely memoize. So if I'm looking for memoization, you know there are two parameters. One is index, the another one is sum. So what do you do for index? You make it for 0 to n minus 1 is the index. So you will be requiring an n size array. The sum is whatever sum is given to you. So you take one more size, sum plus 1. So this is going to be the dp of n sum plus 1. And you know how to memorize this. It's a very simple step. How do you memorize, guys? Come on. Very simple. Now though it's like bread and butter to you. Like you just know it. Equal to. Perfect. And one more line. If dp of index sum not equal to minus 1, return. If that state has not been visited, return. How easy it is to convert a memoization solution. Sorry, to write a memoization solution. So once you've written the memoization solution, can I say now the time complexity is bgo of n into sum, and the space complexity is bgo of n into sum for the matrix plus a bgo of n for an auxiliary stack space. Why an auxiliary stack space? Because of this 1 2 3. So there is 3. This function call will wait. This function call will wait, and then this will be executed. So there is an auxiliary stack space. Lecture 1. I've already taught lecture 1 recursion playlist. What is auxiliary stack space? So done. Next step. Next step. Yes. I don't like this. I don't like auxiliary stack spaces. So what do? You convert this into a tabulation. You convert the recursion into a tabulation because you don't like it, right? So how do you convert this into a tabulation? Very simple. What's the first thing? Base case. Write the base case. What's the next thing? Look at the changed parameters. Look at the changing parameters and write nested loops. And the last step, copy the recursion. Nothing special, just copy the recursion. Okay. So base case. First step, the dp will always be same. So int dp of n sum plus 1. The dp will be same. Okay. Now let's look at the base cases. What are the base cases? Observe this. The first base case says if sum is 0. So if sum is 0, what can be the possible value of indexes? Ask yourself. Index can be 0, 1, 2, 3 till any index, because we are not giving a check on index. We are not giving a check on the index. We are giving a check on the S. So we know one thing. Okay, index can be anything. So thereby, first base case will be, I'm not giving any check on the index. So on any index on 0, I will be having a true. Makes sense. Makes sense. Let's have the next one. We come over here and we are having index equal to 0. So on index equal to 0, when will this guy return a true? On index equal to 0, when will this guy return a 1 rather? When will this guy return a 1? That's my case. By the way, what have I written? Have I written true or false? This will be, by the way, 1. So, as I said, when will this guy, yes, I repeat, when will this index equal to 0 return a true? Only at a of index. Only at a of index. So, there has to be a case where you write at dp of 0 will only be 1 at a of index. That means at a of 0, it will be only 1. But there is a slight stuff. The dp is declared of s plus 1. So just make sure the a of 0 has to be lesser than s in order to this to be executed. Otherwise, it will give you a runtime error. And I did miss this in the lecture dp14. This line. It's very important because you're declaring s plus 1. So if you're just having the second parameter as a of 0, you just need to make sure this. So base cases have been done. Base cases are very simple to write. You just have to observe. Okay, let's move across. Base case is done. What's the next? Look at the changing parameters. Which are the changing parameters? So what are the changing parameters if I ask you? One is index, the other one is, you can say, sum. In the recursion, what is recursion? Recursion is top, down, then accumulate. So where did you start the recursion from? 2, 1, 0. What is tabulation? You start from the base cases, you accumulate. You start from the base cases, you accumulate. Then you take these and form this. That's tabulation. You take these base cases, accumulate. You take these base cases, accumulate. Then you take these base cases, then you accumulate. Bottom up, bottom up. So again, bottom up doesn't means from 0 to 2. Depends. As long as you're starting from base case and you're moving up, that's bottom up. So can I say this? The changing parameters are quite straightforward, and that's index and sum. So where is actually the index running from in the recursion? From n minus 1 to 0. And over here the base case is 0. So the base case is written, this will run from 1 to n minus 1. And the sum will run from 0 to s. This is how you can write the two nested loops. And once you've written this, it's time to copy the recursion. So I can say the next lines will be I equal to 1 till n minus 1 because 0 has been done. And the sum will be 0 till the sum. And these will be the lines. And over here, copy the recurrence. And if I do this, then the extra auxiliary space that we are using will be omitted, and this will be the time and space complexity. So what I'll do is now I'll show you by coding this, and over there we'll copy paste, and then we will do the next step, which is space optimization. So without wasting any time, let's check out the code. Okay, so we are given this num and the target. So what I'll do is I'll just write the function, and we know the function will have index and the sum and the target, and the num array. And the base case was very simple. If you remember, if sum is 0, I'll return as 1. If the index is 0, then you're going to return a of 0 is equal to sum. That's what we're going to return. And there'll be a not take case, which will definitely be f of index minus 1. And sum will go as it is. There will be a take case, which will be 0 initially. But I can definitely pick it up if the array of index is someone who is lesser than equal to the sum that I'm looking for. And if that's the case, the take will be f of index minus 1. And if it picks up, the sum goes lesser by, definitely, it's by the way not a of 0, it will be num of 0. Sum goes lesser than by num of index. And over here, this will be num. At the end of the day, you can say return not take plus take. So this is the recursive solution that does come to my mind. And so over here we just need to figure out n equal to num dot size, and once you have done n equal to num dot size, what's the next thing? We just return f of n minus 1 and the target and the nums. Perfect. And yeah, we have pretty much done it. So let's run this code and see if the recurrence is correct or not. So we see that there is a problem. Yeah, there is a problem because we have not passed the num over here and also over here. So just make sure you pass the num array as well. So I forgot to say why recursion. Now whenever there is a question like count and all these things, it's always better that we try recursion because we're exploring all paths and we have to count all paths. So to explore all the paths, the best thing is recursion. That's why we started with recursion. Okay, so it is giving correct answer, but we know this will give TLE. So let's quickly memoize this. So vector of int dp of definitely n comma vector of int, definitely this will be target plus 1 comma 0, rather minus 1. Just make sure this is declared, and you can just declare the n before this just to avoid something. And over here you can just say vector of int dp, or rather this will be copy pasted here. Perfect. This will pass by reference, and over here you'll just pass the dp, over here you'll just pass the dp, over here you'll just pass the dp, over here memoize the index and the sum, right? and over here it will be dp of index sum. If not equal to -1, return dp of index sum, right? That's how you can easily do it. It does give me the correct answer. Now if I just submit it, it will be fine. So there's a lot of people were saying me, what if the problem says you don't have positive integers and negative integers? So a lot of people were asking me, but Shriver, over here there are positive integers, so you can easily memorize by creating a DP table. So what if there are negative integers? Guys, what is DP doing? For states like index comma sum, DP is basically storing the value of that state. What is the value of index comma state? So you're storing it in a matrix, right? Where index comma sum is an index number. So if the sum goes negative, your doubt is how will this matrix store it, because it cannot have negative indexes. So guys, why are you using matrix? To store. There are a lot of other data structures that can store values of index comma sum. Yes, I've given you the hint. You have to tell me in the comment section if the sum goes negative, what is the data structure that you can use instead of an array to store it. Tell me in the comment section, okay? And in the next video or in the comments only, I'll reply if it's correct, okay? So try it out. Okay, so we've done this. Now what's the next step? The next step we know is dp of best thing to do. Or okay, let's keep it. So what is the next thing? Let's convert this into tabulation as usual. And what do we do? First thing, all the base cases. 0 till n I plus plus. What is the first base case? If dp of I and 0 is, that's 1. What's the next base case? If a of 0 is lesser than equal to tar, instead of okay, it can be tar, and dp of 0 and a of 0 will be 1. Perfect. And write the changing parameters 1 till n, because the base case is at 0, so you start from 1, and the summation will be going from 0 till sum lesser than equal to tar, okay, and sum plus plus. Perfect. So what did I tell you? You don't need to think anything. Yeah, your task is not thinking so much, because you're just moving in the opposite fashion, so it will automatically fill up. Done. Instead of this, dp, okay, instead of this, sum, and erase this. Perfect. What's the next thing? dp of index minus 1, sum minus this. So just fill it up and omit this portion. Perfect. Instead of return, write this. And instead of n minus 1, dp of n minus 1, the call that you made to the recurrence, okay, and omit this. And if you have done this, now try to run it off and see if it is running. By the way, it will be index because you've written everything in terms of index, so it's better if you write everything in terms of index. Now try to run this tabulation code and see if it is running fine or not. Again, I get some mistakes. Probably the mistake is due to array. Yeah, over here it will be no. So just make it dumb. Indeed, it does run. Now let's quickly submit it off. So what's the next step? Space optimization. Can you do a space optimization over here? What is the trick that I've told you in order to recognize if there can be a space optimization? If you have seen all my previous videos, you know. If you see anything like index minus 1 or index plus 1, what's the concept? What is the concept? I'm not going to repeat it. Watch my previous videos. Very simple, yes. Instead of this, just create the row. Previous row of same size, target plus 1 comma 0, and a current row of, so basically just create 2 rows. And instead of dp of I, now this will be the, what will be this? Do you, can I say that for every I equal to 0, yes, for every I equal to 0, it will always be, yes, it will always be true. So what you can say is, instead of this, because what does this signify? I equal to 0. It signifies for every index, is for every index the 0th guy. That means for every row that you're taking, the 0th index, for every row that you're taking, the 0th index, For every row that you're taking, the 0th index will be 1, right? So as of now, you've taken the first guy and the second guy. And the first guy is known as previous. The second guy is known as cur. So just make sure you do it. Instead of this, you say, okay, the first guy, the first row, previous 0 will be 1. And there is another guy, cur 0 will be 1. Perfect. And over here, instead of dp of 0, you know what will be? It will be previous. Yes. That's what you just need to write it. Once you've written this, what are the changes? Instead of index minus 1, that is the previous row. Index minus 1 means the previous row. Done. And what about dp of index? That's the current row. Once you've done this, can I say the previous will be equal to current? I can. And over here, what will be dp of index minus 1? That's the previous or current, you can take it. And if you just submit this, you will see this is also running absolutely fine. And if I submit this, it will be giving me the correct answer. But the question is, did we optimize in time? Obviously not. We just optimize the space that we're using. Now a 2D array is not being used. We're just using an 1D array. Again, if these are negative numbers, you can use the data structure that I was discussing, or in the comment section you'll find the answer. So guys, I want you guys to write in the comment section, what if these were negative numbers, which data structure will you use? I want you to write that in the comment section. So guys, I hope you have understood the entire explanation. Just in case you did, please make sure you like this video, and if you're new to the channel, do consider subscribing to us. And to continue our tradition, please do comment understood under the comment section, so that I get motivation that you are understanding whatever I am explaining. So with this, I'll be wrapping up this video. Let's meet in the next one, where we will be discussing the next problem from the DP playlist. Till then, bye bye, take care.
Whenever your heart is broken.